We're going to talk today a little bit about circular motion. Circular motion. And this kind of assumes that you're familiar with distances and speeds and forces and accelerations in straight lines, like this, like a car speeding up or slowing down. Here's the problem. If I have a rock that is tied with a piece of string and I hold on to that rock right over here and I start spinning it around my head faster and faster and faster. There's my hand holding on to that, and the rock begins to spin around and around and around. What happens to the rock when I let go of it? So let's think about it. Does it keep circling? Does it go out in circles until gravity makes it fall to the ground? So its motion would look something like this. Or does it go straight until gravity makes it fall to the ground? So pause the video, think about it for a minute, write down your answer and an explanation of why you think so. And then start up the video again and let's talk about it a little bit. Okay, so when we're talking here about motion, we want to know about this rock's change in direction, its change in velocity. So when we talk about accelerations and forces, we're talking about an acceleration, meaning a change in the velocity vector with a change in time. And that's really easy to see in straight lines if you have a car and you apply a force to it. If you hit the gas, your car goes forward. It accelerates forward, and if you hit the brakes, your car slows down. There's a force opposing its motion, which makes it slow down. But that's not so obvious when we're talking about a circle. Okay? So, Newton's second law states that to accelerate something of a given mass, we have to apply a force to it. Otherwise, it just sits there and does nothing. Just like hitting the gas pushes the car forward, and hitting the brakes slows it down, something is changing to make our rock change its direction as you're spinning it around over your head. You're not changing the velocity, magnitude at all. You're changing the direction, the vector of the velocity. Okay? So let's draw a picture here, because being able to do physics really well means that you're drawing good pictures. So let's take a look at our rock at several positions in time. So here is my rock when I start. Here's my string with a nice little bow tied on it. And there's my string. And there's my hand holding it right here. This is when I start moving it. Now, at a later point in time, oh, hang on a second. When you take a look at this, let's say I took a strobe picture of this. Right at this moment, if you looked at this rock, you would see that the velocity was heading in that direction. So if I took a picture at a later point in time, here's my same string. This is a little bit in time later. Here is my rock that's tied on there. But now the velocity is actually heading this way. Now if I continue doing that over periods of time, there's my rock and my little string, and now the velocity is headed in this direction. While there's no change in the magnitude of the velocity, there's a change in its direction. See how it's pointing up this way the first time? A little later it's going this way, a little later that it's going this way. If it's changing its direction, then it has to have some sort of force acting on it. That's what Newton's laws say, Newton's second law. So if you go through and if you remember about adding and subtracting vectors, if I take this little velocity vector here and I want to find the difference in the velocity vector in a given amount of time as its acceleration, I would take this velocity vector and I would subtract the other velocity vector, or you could do it the other way. You could subtract, you could start with this velocity vector and subtract this one from it. What you'll find is that the change in velocity of that resultant vector it actually points inward. And I'm not going to go through a lot of detail in talking about why, because then we get kind of bogged down in the math. And this is an idea of how to explain the thinking process of understanding what happens to that rock, being able to visualize it or to puzzle through what's going on there. So that resultant vector now points inward. If that resultant vector, that acceleration, is pointing inward, here's the center, here is my rock going around in a circle, there's my string. That acceleration is heading this way because that was the change in the velocity vector in a given time. Therefore, the force, Newton's law says, must also act in that direction. And this is what we call rotational or centripetal force. Okay, now Newton's law also says, and Newton's third law says that for every action, there's an equal and opposite reaction. So this means that if there's an inward force keeping the rock going from flying off, then if you take that force away, if that force disappears, like when you let go or the string breaks, there's nothing to oppose the motion of this rock. And it must go out straight and tangentially here. Otherwise, you'd have to have a force acting on it to push it back in or push it down. We're not talking about gravity right now. Eventually, that rock will fly off and gravity will push it down to the ground. But we're imagining we're looking top down at a person spinning this rock over and over around their head. Now, let's think about this in a slightly different way. If you go back to some of your stories, this kind of explains how David could swing a rock around and around and around over his head. And when he let go of that rock and it went flying off, it hit the giant right in the head. Right there is my rock. That's one way to think about it, but to really understand physics, it's a great idea to do experiments. So I suggest go outside and give this a try. Take a string, take a rock, invite a friend to come out or take a video of it, and try doing this several times and watch what happens. You'll see that that rock flies straight forward. If you want a more serious analysis of the vector forces, there's probably lots of other good videos on the web that can explain that to you. Maybe I'll even make a video on it sometime. But that explains kind of theoretically and an application of how you think about the world, why that rock should fly straight off. I hope that makes sense. I hope that helps. Bye.